Okay, class, what we're going to be talking about today is the space inside of parallelograms, or maybe you want to say the area inside of parallelograms. If we flip to the objectives page, um, the first objective is proving why the area of a triangle is 1/2 the area of a parallelogram. Second, prove why the area of a parallelogram is equal to the area of a rectangle. The first objective is review. We'll probably skip that for time's sake. Um, but we will cover um, proving why the area of a parallelogram is equal to the area of a rectangle. And then third objective, find the area of a parallelogram and use the formula for area. Um, if we go here to objective 2 and look at how do we prove that the area of a parallelogram is equal to that of the area of a rectangle, what we want to do here is let's label the 4 vertices A, B, C, D. And if we draw an altitude from vertex A intersecting segment DC, remembering an altitude is a segment that's perpendicular to the base here. When we draw that segment, and if we focus on triangle ARD, I'll shade it here in green. If you can imagine taking this green triangle, cutting that green triangle off with scissors, and repasting that triangle right over here in blue, and then looking at that, what we just made was a rectangle, and now I'll shade that rectangle in blue. I'll say that again. So if we draw altitude AR, a segment that's perpendicular to the base here, remembering that we have a parallelogram here, but we chop off that green right triangle, and then we reattach it over here in blue, okay? Reattaching it as the blue triangle, and if we shade the new shape, I'll shade the whole shape in blue, so we're not focusing on the green right triangle anymore. It's as if we cut it off with scissors, we would arrive at this blue rectangle. So two things just happened. We cut off this right triangle, reattached it over on the right side, creating this blue rectangle. So now we need to recall the formula for space inside of a rectangle, which is area equals base times altitude, or maybe your teacher says area equals base times height, which now we realize that the formula for the space inside of a rectangle has to be the same as the area of a parallelogram. They're two in the same formulas. Why is that? Because if we start out with that parallelogram, cut off that green right triangle, reattach it on the other side, we created a rectangle. So the formula to find the space inside of a parallelogram is the same as the formula for space inside of a rectangle. Okay. Let's go through some examples. Okay, look at the directions read. Find the area of each parallelogram, looking at letter A as an example. Again, recalling that the area of a parallelogram is the same as the area formula for a rectangle, and we just discussed why that is. So the space inside of a parallelogram is going to be base times altitude. They're asking you to find the area. We know the base length is 8. We know the altitude is 12. So the area of this parallelogram is going to be 96 square yards. 96 square yards. Understanding that in this case the altitude was interior of the parallelogram. If we go on to example B, hopefully you realize in example B that in this case the altitude of the parallelogram is exterior to the parallelogram, okay? And the base of the parallelogram is here. So to find the space inside of the shaded parallelogram, it's going to be the base length of 14 times the altitude of 14. So we got the area equals 196 square feet. Okay. In part C, I'll leave part C for you if you want to work on that. I'm going to come back to that and find the area of that parallelogram. Now moving on to example 3, it says given the area of each parallelogram, find the missing measure or missing dimension. Okay, so in letter A, again working off what we know that this is a parallelogram. So the formula used to find the space inside of a parallelogram is area equals base times altitude. We know what the area is, so we're substituting 72 square inches in for the area. We know the base length is 12, and we're looking for the altitude of the parallelogram. So the inverse of multiplying by 12 is dividing both sides by 12. So the altitude of the parallelogram has to be 6 inches. Okay, 6 inches for the altitude there. Okay, going on, I'll leave part B if you want to come back and try that later. Again, this is a parallelogram. So the space inside of a parallelogram is area equals base times altitude. We know the area is 30 square meters, so substituting 30 into the proper place. We know in this case the altitude is 5, and we're looking for the base length, actually, is what we're looking for. So the altitude is 5, and we're looking for the base length. So we divide both sides by 5, and we get the base length is equal to 6 meters. 6 meters there. Okay, fourth objective. And maybe that's not on the objective page. I just noticed that, but there is a fourth objective, and the fourth thing we need to learn today is how to find the area of a rhombus. And what I want you to think of is, what is a rhombus? Well, a rhombus is basically those cool things in the summer. I know you guys all fly in the summer when it's nice and windy out, or in the fall. You get it out and you fly it around in the air, and you have a lot of fun. They're called kites. Um, so a kite is actually a rhombus. So if you were trying to construct your own type of kite, because you're pretty tech savvy, you want to find out how much material you need to make a certain kind of kite that you want to fly. What we're going to do is we're going to find the length of one diagonal. Okay, we're going to multiply that by the length of the other diagonal. Then we're going to take half of that. So if we're looking here in part A, the length of this diagonal, recalling that a diagonal is a segment that starts at one vertex and intersects the opposite vertex. So in blue we have one diagonal, which is 14 inches in length. Okay, so we're going to take 14, then we're going to find the length of the other diagonal, which would be 10 inches. We're going to take 14 times 10, we're going to multiply those, which is going to give us 140. Then we'll take half of that. Okay, so 14 times 10 is 140. And a half of 140 is 70. So the space inside of this rhombus is 70 square inches. Or if you were making a kite, you need 70 square inches of material to make your kite. Okay, let's go back. Let's take a look at example B. Again, how much material do we need to make this kite? We need to find the length of this diagonal. Well, the length of that diagonal is definitely going to be 9 plus 9. Okay, so we got to keep that in mind. And then the length of this diagonal is going to be 6 plus 6. So we need to do some addition here. So the material needed to make this kite is going to be 9 plus 9, which is 18, times 6 plus 6, which is 12. And then we'll take half of that. So off to the side, I got to do a little work here. 18 times 12, 8 times 2, 16, carry the 1. 2 times 1 is 2, plus 1 is 3. 1 times 8 is 8. 1 times 1 is 1. We got 6. 8 plus 3 is 11. Carry the 1, 2, 16. So the space inside of this rhombus is 1/2 of 216. So the material needed to make this kite would be 108 square meters. 108 square meters there. Okay. Okay, again, these are just more problems involving finding the area of each of these rhombuses. Let's look here and do this one example, how to find the area of this rhombus. It's a little more challenging because the space inside of this rhombus, we first got to find the length of that diagonal, which is going to be 20. Okay, by taking 10 plus 10, it's going to give us 20. And we need to multiply that by the length of this diagonal. Well, the problem with this is we don't know the length of that red segment, nor do we know the length of half of it where we could double it. So what we need to do is we're going to pull out this right triangle. How do I know that's a right triangle? Because in a rhombus, from chapter 6, we learned that the diagonals are perpendicular bisectors of each other. So if we pull out this triangle, I'm going to try and keep the colors. We got our blue segment, we got red, and the hypotenuse to the right triangle is 26. Okay, and we know the blue segment, which is a leg in the right triangle, is 10. We need to find the length of the red segment. When we get that, we'll double that to get the length of the diagonal in the triangle there. Okay, so now we'll call this x. So using Pythagorean's theorem, we're going to go hypotenuse squared, which is 26, equals leg squared, 10, plus the other leg squared, okay, 26 squared. It's going to be 26 times 26. 6 times 6 is 36. Carry the 3. It's 15. 2 times 6 is 12. Carry the 1. 5. We got a 5 there. So we got 6, 7, 676. 26 squared is 676. So we got 676 equals 10 squared is 100 plus x squared. Subtract 100 from both sides. So we get 576 equals x squared. Take the square root of both sides. And we get x equals, let's see, 5, 12, got to be 20, is it 24? It's got to be 20, I believe that's 24 units. Let me double check myself. 24 times 24, that makes sense. 26, 625, yep, I believe that's 24 units. So the length of the red segment is going to be 24 units. So to get the length of the red diagonal in the rhombus is going to be 24 times 2. So it's going to be 48 units for the length of the red segment in the rhombus. We have now found the length of the other diagonal in the rhombus, so we can now find the area of the rhombus. Remembering the length of the one diagonal, which is in blue, is 10 plus 10, which is 20. Times the length of the other diagonal, which is 48. So the space inside of this rhombus is going to be 1/2 of whatever 20 times 48 is. Well, 10 times 48 is 480. And if you double 480, you get 960. So half of 960, half of 900 is 450. Half of 60 is 30. 480 square units. Okay, so 480 square units will be the area inside that rhombus. I believe that's all we have for today. Let's double check. But I believe we completed the lesson. There's one more problem where you're finding a composite area. We've done that before. If you want to try and work on that problem here, it's finding the area of a rhombus and then finding the area of a right triangle and then adding those together. Same here in part B, finding the area of a rectangle and finding the area of a parallelogram and adding those composite values together. Thank you for tuning in.